the really interesting thing about the likelihood ratio test is this result here. It's surprisingly simple, and it's very similar to the formulas we have, for example, for computing confidence interval for the mean. It works under the same assumption. So we need that we have a reasonably large number of data samples, not 10, but 100 or more. Millions are even better. And that the central limit theorem holds, which concretely means that the model assumes distribution with a finite variance. We'll come back to infinite variance in the next module. Right now, we need to assume this. If this can be assumed, then we have a radical simplification, which is the following. It says that the likelihood ratio statistic, which is obtained by taking the difference of the log likelihood of two estimations, one that gives theta hat 0 under the H0 hypothesis, the other one that gives theta hat under the more general model, then the distribution of this under H0 is a pivot, which means a bit more. It means that, in fact, the p-value is exactly equal to this quantity applied to the function 1 minus the CDF of the chi-square distribution. Chi-square is one distribution derived from the normal distribution. It's the sum of n independent squared random Gaussian variables with zero mean. It's a very well-known distribution in statistics, so it's available in all packages and tables. So we take 2 times the likelihood ratio statistics, and 1 minus this gives approximately the p-value. So in other words, it means that it means that the distribution of the likelihood ratio statistics, or if you want 2 times the likelihood ratio statistics, has approximately a chi-square distribution. So finding the probability that this is larger than something is the same as taking the CDF. What is, here there is a little p, it's not the same as the p-value. P is the order of the test. It is the number of dimensions that H1 adds to H0. So this is valid when we have parameter theta, which is a continuous parameter, like we had in all the examples before. We had, for example, mu and sigma. So we count how many degrees of freedom, how many dimensions we have to the parameter, how many continuous independent values of the parameters do we have under H0 and under the global model, and the difference, that's the key integer that we need to use as input here for this thing. This is derived also from the central limit theorem. Don't give the proof, but I give references for the proofs in the lecture note. Instead, let's applying to some of the examples we've done before. Here I have a variant of the test I did before where I have 2 samples, but they are not paired. I want to know whether blue is better than red. In the previous example we saw half an hour ago, the data experiments were paired, so we could simply take the difference or the ratio, and then it was a very simple experiment. Here they are not. We have 2 clouds that were done independently because we could not reproduce exactly the same setting. For example, because I'm measuring things on the internet, when I measure with the blue conditions, I cannot measure at the same time under the red condition. I have to measure at another point in time. So hopefully everything has been properly randomized, the hidden factors have been scrutinized, and we obtain in 3 different scenarios, we obtain these 3 clouds of points. One way to model this is to say I model the blue points, the x, for example, as being some value, mu1, plus noise, and the same for the red point. So I have an x set of data and a y set of data here. And then one of the models that is often used for analysis of variance assumes that the error terms, the epsilons, are all drawn from the same Gaussian distribution with same variance. It's not something I like very much, but I'm doing it here to show you this classical test that is done. And then the null hypothesis is they have the same mu for the 2 or not. So this is, again, a very strong set of assumptions we're making. We're assuming the data comes from a Gaussian distribution with same variance in two cases. In some of the homeworks I ask you to solve, you will be able to do other cases when we don't have necessarily the Gaussian assumption. But here, the Gaussian assumption makes all the computations very simple. So what is the theory saying? The theory says, well, under H0, you estimate the parameters of the model. So the parameters of the model are the sigma and the mu, which is the same, mu1 and the mu2. And under H1, you need to estimate, under H1, you have mu1 that is a different parameter than mu2. You have two parameters to estimate. I'm not giving the computations here. It's very similar to the computations we did half an hour ago when we had, you write the likelihoods, you take the log, you have the big Gaussian formula, you have an optimization problem to solve. In the first case with two variables, mu, the common value, and sigma. In the second case with three values, mu1, mu2, and sigma. But since everything is linear, the solutions are given by big projection that here have closed form. And the likelihood, the log likelihood, is related to the estimated variance, which in this framework is classically interpreted as the norm of the residuals under H0. It's the norm of the errors under H0. And this is called SS0, classically, for this type of test. So sum of squares. So is the norm of the residuals if we accept H0. And SS1 is if we accept H1. Which one should be smaller? Yes?
SS0 should be smaller?
No. So when we estimate the model, right, if we have, so there's two ways to think of it. So the intuitive way, the ANOVA way, consists saying, if I estimate under H1, I have more degrees of freedom. So my estimate of the errors will be smaller, because under H1, I allow the mean of the blue to be different than the mean of the red. So what are we doing here? We're doing a least square estimation of this cloud by forcing the line to be horizontal. Graphically, that's what we're doing here. So I need to draw a horizontal line in the middle of the blue cloud and in the red cloud and compute the sum of the errors of the square distances to the line that I've drawn. Right? If I have two lines, the sum of the errors will be smaller because I have one more degree of freedom. It's an optimization problem. Find the position of the line such that the sum of the square errors are different. Under H0, I'm constrained to have one single line. Under H1, I have two lines. So the solution under H0 is a feasible solution for H1. So its score cannot be better than the optimal score here. So we always do better under the big model. But the question is by how much? If the improvement is small, which means if this ratio, if both are the same, this ratio will be 1, so the log will be 0. If S0 is much larger than S1, this thing will be large here. And if it's large, that means that H0 is not true because, it will mean that, yes, the reduction I have when I have H1 is considerable. Therefore, H0 was not true. If I allow myself to have a mu1 different than mu2, I have something very, very different here. Another way to think about it is that we're maximizing the likelihood, and the likelihood is minus the log of the SS0 multiplied by some constant. So maximizing the likelihood is minimizing the sum of residuals here. Again, this is called ANOVA because everything can be distilled to comparing whether a ratio of sum of squares is large or not here. But now, if we apply our theory, we can have a very, very specific result. The only job that we have to do is to compute P. How many degrees of freedom is there in H1 and in H0? So in H0, we need to estimate 1 mu and 1 sigma. So we have 2 degrees of freedom. In H1, we have 3 degrees of freedom. We need to estimate mu1 and mu2 and 1 sigma. so the difference is 1 here. Therefore, the p-value is 1 minus q1 square of 2 times this quantity here, which is n over 2 log SS0 over SS1. Incidentally, if I would have the same model, but I am not assuming the same sigma for the two, then the method would work exactly the same way. I can estimate the sigma of the blue, the sigma of the red, and I don't have to force them to be the same then, but of course, I will have different SS0 and SS1 that will be computed, and at least SS1 will be different. And the number of degrees of freedom, the difference would be 2 instead of 1, if I have 2 sigmas to estimate under H1. So this method is completely generic. We don't have to stick to those oversimplifying assumptions that are done with ANOVAs typically. Right? So I applied this here, and I obtained for these 3 parameter sets the 3 p-values that are obtained with these asymptotic formulas here. It turns out that for this model, if we believe in the assumptions of the Gaussian, everything is Gaussian, everything has same variance, as we can expect, there are closed-form formulas with the help of projection matrices. And so this is done typically by MATLAB using functions, or NumPy using functions that are called ANOVA. So a keyword of ANOVA. There are many variants of ANOVA. ANOVA means whenever we have a model that is linear with respect to the parameters and same variance for everyone. There are different ways to present it. Here is one way to present it here. This is what ANOVA would give exactly, and assuming the assumptions are correct, we can compute exactly the p-values, not asymptotically, but exactly, and they are given here under those, for those 3 examples. So we can consider them the true value if the model is correct, and we find that they are very close, at least for practical purposes, right? So the results of the test is the same whether we use the approximate formula or not. By the way, for which parameter sets do you conclude that blue is different than red? Yes, the correct value is D. So the thing to remember is reject H0 when P is small. If P is small, you reject H0. So certainly here we reject H0. Here probably also, if we believe like statisticians that small means 0.05, less than 0.05, and here certainly we don't. Now the other thing to translate is what does it mean to reject H0? H0 means they are the same. So reject means declaring they are different. So we declare that they are different in the first 2 cases. Here, statistically, those 2 clouds don't come from the same mean. Here, it seems like they come from the same mean here. This is what tests will tell you. We can compare 2 confidence intervals. Here I computed a confidence interval for blue and for red separately. There's no sense in taking the difference because the data are not paired. So I take the confidence interval for the mean in the first 2 cases. And we see that in the first case they are very different, which corresponds to the fact that the p-value is also very, very small. So it's a very clear case. The other one is also very clear that there is not much difference. So it's another clear case. And then in the case in between, this is where tests really perhaps are able to disambiguate things. Here it says reject H0, whereas the confidence interval are largely overlapping. So this is what tests can be used for when we're in the gray zone. This is the chi-square distribution that I mentioned. It's the square of the sum of n independent random variables that are 0 mean and standard deviation equal to n. So it's a positive random variable. It's always positive. Its mean is n and its variance is 2n. And here are the 99% points, for example. We see they increase with n. So that is one of the collection of magical numbers that we have in statistics. Now that we know this asymptotic result, we are able to do a more sophisticated test than the one we did before Before, I tested whether some data comes from a known distribution after binning. But I was not able to do much for computing the p-value other than by simulation, because it didn't have a closed form. But in fact, it has an approximate form, and then this approximation will be useful in particular if we're doing what is called a composite goodness of fit test. So composite means I'm not just testing for one distribution, but for a hypothesis about the distribution. For example, is this data coming from a Gaussian distribution? When I say that, I'm not testing a specific Gaussian distribution, but a family of distributions. So the test says, is it true that the data comes from a parametric family that has some parameter theta? For Gaussian, it would be the mean, mu, and sigma, the joint sigma of all of them. So we do the same as before. We bin the data, and we obtain Ni. If it is true that H0 holds, then we're able to compute the vector Q of theta, which is the probability that an arbitrary point falls into bin I of the histogram, at least numerically. If I have a Gaussian distribution, I need to compute what's the probability of a Gaussian distribution being between 0,1 and 0,2, for example. I can compute that once I know at least the theta. So for every theta, there's a well-known vector, Q of theta, that gives me the distribution of n, which is multinomial. This is the number of times we fall in bin I when we have capital I possible choices given by this probability distribution. And this is the null hypothesis. The generic hypothesis, like before, is that the distribution P is anything, any distribution that we can allocate to the bins here. So let's do a likelihood ratio test. Under H0, we need to compute the supremum of the likelihood of Q of theta given the model we have before. And here it is something that can be solved only numerically. So it's I have to pose an optimization problem, which depends on the formula theta. We know exactly the form of the distribution here, right? It is sum of the ni log qi of theta. So I have to maximize this function that is parameterized by theta. So in general, it might be a non-convex problem, but if the dimension of theta is not very large, it will not be a difficult problem here. So let's come back. Whoops. Here we are. So I take so this is for every theta, this is my likelihood. I need to find the theta hat that maximizes sum of ni log of q, where ni is given by the data. And as usual, under H1, we find this ni divided by n is my maximum likelihood estimate of the probability of falling in bin I. And then the likelihood ratio statistics is the difference of the logs, gives me that thing here. And the p-value is then the supremum over theta 0, like before, of all that stuff here. When theta 0 is a single value, we can do Monte Carlo. Otherwise, then a simpler thing is to use the asymptotic result. If the number of data points we have is not very small, we know that this is approximately chi-square p, where p is the number of degrees of freedom that is the difference between H0 to H1. Right? For example, I did that for Mendel's p's, and I obtained with this asymptotic result 0.89. My Monte Carlo estimate was 0.92. This is within the confidence interval of that, so the two are consistent. The two methods gives consistent values here. Right? Now the only work that we need to do when applying this method is finding the dimension. In this case, what is P? So in the generic term, in the generic case, when I have I bins, K0 is the dimension of the parameter under H0, which is the dimension of the parameter theta. What is your solution? Well, let's look at the solution. It's very simple once we do it by steps. What is the dimension of the parameter set when we're under theta 0? Under theta 0, it's whatever the dimension of theta 0 is. If we're testing for Gaussian, it's 2 parameters. If we're testing for exponential, it's 1 parameter. So it's k0, the dimension of theta 0. Now, under theta, we have to pick a parameter p, right, which is anything satisfying the set sum of the, so it is I numbers, where I is the number of bins, but there's a constraint. The sum of the pi is equal to 1. So in fact, we have to find I minus 1. I minus 1 degrees of freedom. So that's the difference here. Let me apply this to the apparently simple but important problem of testing whether a distribution is normal. As you will see, this problem doesn't have an exact solution, but it has a number of approximates. So I have this. If you remember, we had several cases. Case where it was obviously non-Gaussian, and there was this one here where perhaps yes, perhaps no. So let's do a test. So the first idea is to apply the composite goodness of fit test by binning the data into 10 bins. Why 10? Well, because MATLAB does it, so let's do it too. So let's look at first method. This is Homer's method. So Homer estimates mu and sigma by least square fitting a straight line to the QQ plot. This is what MATLAB does. That's the red line here. So if we look at the doc of QQ-plot, perhaps we find the parameters here. Otherwise, we can do it numerically ourselves. Homer obtained those values for mu and sigma. So mu will be the offset, and sigma will be the slope. Then he compares it to the histogram. He compares, the histogram to the theoretical value that would be obtained with mu hat and sigma hat. So we do a histogram with the values we have here. So we bin whatever MATLAB has decided to bin for us. We find those values, which of course are integers. There's a number of points that fall in each of the bins. And then I compare the theoretical values I would obtain if I would take mu and sigma, those values. Those theoretical values are obtained from the CDF of the Gaussian distribution. I know the mu and sigma of the Gaussian distribution. I know the bins. They are not shown here, but they must be known. For example, perhaps this is the bin between -3 and -2. So between -3 and between -3 and -1, perhaps there are 7 values. What is the probability of a Gaussian falling there? It is the CDF of -1 minus the CDF of -3. Then I compute the likelihood ratio statistic. I compute the number of degrees of freedom difference, and I compute the p-value here. The p-value is small, therefore I say it is not Gaussian here. This is what Homer did, right? First method. Second method. Well, Lisa, who is usually smarter, if you know the Simpsons cartoon, but we have to be careful. Even smart people sometimes are wrong. Lisa observed that Homer did not apply a composite goodness of fit test since he first fitted the data to obtain mu sigma, then compared the data to the fitted distribution, right? So, because the composite goodness of fit test requires that the parameter qi of every bin are fitted by maximum likelihood. That's the textbook method we see. First you fit according to the maximum likelihood principle, then you compare to under H0, under H1 here. So what she does instead is the values of the 10 bins are generated by multinomial n10q. With qi, the probability that the normal falls in bin I, and mu sigma are, this is H0, of course. This is H0 and H1. So what Lisa did, she fitted the model under H0 and under H1 and computed the log likelihoods, right? So let's do that. That's what we saw before. We need to maximize this, where Qi of mu sigma is the probability that something falls in the bin. So the bin is bi minus 1 bi. N is the shorthand notation that I use all throughout this lecture for the CDF. So identify a probability distribution with a CDF. So that's the CDF of the Gaussian. And this, if I know mu and sigma, that's the probability of falling here. Right. So by doing this, we obtain exactly the Qi. Then I have, of course, this is a highly non-convex problem. The function n is convex on some part, concave on some other, and is not even known in a closed form, other than declaring that n is one of the elementary functions. But numerically, we can do it if we have only two parameters, mu and sigma. Anything that is small dimension is never too hard to do, right? How do you solve that if you have to solve it? Well, you can ask F-min search. That will, so it means you call for a black box. In the worst case, I mean, you could discretize your values between 100,000 value in X, in mu, as many in sigma. Then we'll have 10 to the power 10 values, and you run it on a cluster for several days, and then you will obtain this. So they are, this is the maximum likelihood fitting of this model. And that gives the following theoretical values for the corresponding bins that are given here. So we do the same as Homer, but the values are obtained not from least square fitting the histogram, but by maximum likelihood estimation here. The likelihood ratio statistic is not that. And now find that the p-value is large. P-value is large, which means we accept H0. H0 says the data is normal. So Lisa's test says the data is normal. Right. Let's look at Bart's methods now here. Bart, who's junior, his small brother, like all younger kids, they cheat on their older brothers and sisters. So he cheated on Lisa, but he is very impatient. He wants to do things very quickly. So he just copied the beginning of her method. He saw that Lisa's distribution is optimal for those two values. So if it is Gaussian, here are the parameters of the Gaussian distribution, at least within the context of this test that we're doing here. And then he did the following. He did a simple goodness of fit test by testing this against the general value. Right. So here I'm saying this is not an arbitrary distribution. This is this Gaussian distribution that have been estimated by Lisa. Then he does it. He finds a p-value. Now the number of degrees of freedom is 9, the difference. We have 10. That's the formula that I've asked in the quiz, right? Now we have 2 degrees of freedom that have disappeared from H0 because we assume they're given by an out-of-band oracle. This is the p-value we obtain here. Then this is a mistake that sometimes we're forced to do. Here what Lisa did was the right thing to do, at least according to the textbook, within this context here. So she did, but we saw that this involved solving an optimization problem that's a bit ugly. So if you want to avoid solving the optimization problem, you say, let me first estimate the mu and sigma, which is fairly easy for a Gaussian distribution, by whatever method, the histogram or anything, and then compare this mu and sigma against the distribution here. If we do this in any arbitrary fashion, that may be completely wrong. This is Homer's method. That is completely wrong. If we do it right, this is right, of course, because we do it right according to the theory. If we do it almost right. That means we estimate mu in a consistent way. We estimate it according to the way the test is working, but then we ignore the fact that it has been estimated. I consider the first step as an oracle. It says, no, I know if it's Gaussian, it is this, therefore I test against this. When we do this, we are cheating a bit in the sense of statistics, and the general theory says if we do this, we know in what sense the p-value is obtained. The p-value is overestimated because the fit is better because we have taken exactly the distribution that has been fitted from the data. Right. So the take-home message is if we estimate some parameter and pretend it is a priori known, then we overestimate the p-value. It's useful to know if we're in a case where the p-value is very, very small, and we know we overestimated, well, we know the true p-value is even smaller. So then we don't need to refine our methodology. This is what we can do. So this is at least one solution for finding whether it's Gaussian. So for this data, at least using this methodology, there is no evidence that it's non-Gaussian. But we could criticize this data, this method. At least it's sound, but there is something we could criticize. There is some arbitrary step we did in this method. Which one? If I sell that to you, there's nothing that you would be worried about. Yes?
The number of bins.
The number of bins and the position of the bins. Right? Where are the bins? They're not given by God. I have a continuous distribution. So where are the bins? To do this right, we should have pre-specified bins. The bin should not depend on the data, otherwise we have again the problem of fitting the bits to, we can make the bins such that they fall exactly in the data here. So that's one of the issues here. It's very convenient because it transforms something that is very complex, if the distribution can be anything, into something that's simple, even simple-minded, but it is a bit arbitrary. So if it's for a category of problems where the data are more likely to fall always in the same region, then there can be well-known bins that do the job once for all. But in general, that's a non-satisfactory principle. Therefore, there has been other tests that have been developed, but they don't have, all of those tests have problems either. So, except in some simple cases. The simple case is a simple goodness of fit test. For the composite goodness of fit, we don't have things that are really much better than the one we have shown. But for simple goodness of fit, there are other tests. So one of them is, for example, the Kolmogorov-Smirnov. That will sound familiar to us, at least once we look at the detail. So here again, we want to test that some data is IID from some distribution versus from any other arbitrary distribution here. And then the object that we consider is the empirical histogram. The empirical histogram, we can treat it as a function of x, f hat of x, which says how many points fall below x. That's what we do when we plot the empirical histogram, which will have a staircase shape. Then if we consider this quantity, the maximum deviation between the histogram that we have here and the true thing we would have if the distribution would be f here. Then, if the true distribution is f, we know in fact the distribution of that. That should not surprise us. Why is that? If we assume the true, so we're under H0, so if we assume the true distribution is f, what we're interested in is what is the distribution. To compute a p-value, we would compute what is the distribution of f of capital X minus f hat of capital X, where f hat is fixed, and capital X is a hypothetical replay experiment here. Right? No, sorry, f hat is not fixed, so I do a replay experiment, I recompute the new f hat, and I compute the value supreme of this, this t, which is the maximum difference between this curve and this one here, if the little x, I'm confused because I'm used the little x, I did something that I should not do, I used the little x, which is here a dummy variable with the same meaning as here. So, given the data xi, this f hat is my empirical histogram. This is the theoretical CDF. It's a well-known curve given once for all. And I look at what is the maximum deviation between those two curves. What is random in this is the second curve here. This curve is random and depends on the data. Right. Now the question is what happens if to compute the p-value, I will draw randomly this from a hypothetical replay experiment. Now we know when we take the transformation of a random variable by its CDF, we obtain something that always has the same distribution, which is uniform. That's a trick we've used several times. We use it for sampling, for example. So here it's the same thing. If I apply the f not to x itself, but if I apply the empirical histogram here, I will have something that has a distribution that's independent of f itself here. Now this distribution is very contorted, doesn't have a closed form, but it's always the same, right? Regardless of the distribution f here. For the same reason that if I take capital X, a random variable that has distribution capital F, the random variable capital F of capital X has always the same distribution. In the second case I gave, it's very simple, it's uniform. In this case, it's more complicated. But by similar arguments as we saw when we discussed sampling, it can be shown that the distribution is always the same. So for example, we can take for f a uniform random variable between 0 and 1, and we can compute this, so that has been done, and software packages have numerical methods, which are not based on Monte Carlo, but analytical method, to compute exactly the distribution of this. Since the distribution is known, I can compute the p-value. I compute this, I look into the table of this, what is called the Kolmogorov-Smirnov distribution, and I will obtain the p-value here. Right. So this is the justification of why the distribution is always the same here, and it's using the trick that if I apply to a random variable x that has a distribution f, then the resulting u has a uniform distribution. So the uniform distribution can be used for obtaining the final distribution. We know some asymptotics, if we're interested. When n is large, we know the asymptotic of this distribution here. For every n, there is a different distribution here, like for chi-square. So let's do the Kolmogorov-Smirnov test with the fitted data. Here I'm cheating, I'm doing with the fitted data. So I have here two distributions where I'm asking, are they Gaussian? So I use the least square red line, and I do the Kolmogorov-Smirnov test to declare whether they are Gaussian or not. Then for the diagram on the left, we obtain a p-value which is declared as 0. In fact, it's very, very small. And on the right, we obtain a value which is 0.29, which is not small. So on the left, we will reject H0. We'll say it is not Gaussian, which is not very helpful. That was obvious from the beginning. And on the right, we will say, yes, it is here. Here I cheated. What mistake did I do? I used the Kolmogorov-Smirnov with the distribution that is fitted from the data, not by a distribution that is given a priori. So by doing that, we know the p-value is increased. We have a p-value that is larger than the true p-value. So in this case, that means no problem. Here, the true p-value is a bit smaller, or is smaller. Now, there are corrections that have been done. They are not really justified by hard mathematical theories, but empirical corrections that have been found to work well. So there is another test than Kolmogorov-Smirnov, which is specific of Gaussian, which is called the Lilliefors test, which does the thing right, at least empirically, by correcting the p-value for the fact that I've estimated the p-value, the Gaussian distribution. If I do it with the Lilliefors test, I find here with 4 decimals, I find exactly the same values. So at least in that case, this doesn't impact the decision. And that's pretty much the state of the art for testing whether something is Gaussian. So there is the idea of Kolmogorov-Smirnov corrected for this thing and it gives Lilliefors here. There are variants. Instead of using the absolute value, you can take the mean square value between the 2 histograms. There are a few variants, but they're essentially giving the same results. So if you need, for whatever reason, to test whether something is Gaussian, as long as you can be convinced it's ID, we do have a solution here. Okay, I think I will close here for today. Tomorrow we'll see 1 or 2 other simple tests that are called robust, will not surprise us. And then we will start the module on model fitting number 2. We'll continue model fitting with more exotic things.